A current I flows in the long straight wire with cross section having the form of a thin half ring. So actually I'll show you how this diagram is visible. It's like a semi-cylinder. It is like this. Okay, it is like this. It's a semi-cylinder. So we are showing only the cross sectional of the like this. Okay, we are showing only the cross sectional front part of the uh, this setup, and they are saying the current is going along the length, means it's going inside. I've drawn like this dotted way. The current is going inside. Okay, so the current is cross. You can take a cross. It is going. No, I have taken outside actually. You can take a dot. So all these things, the current is uniformly going in this part along the inside length of the circular cross section, semicircular cross section. Okay. So how to solve for the magnetic field at point O? So what I've taken is, first I've taken a very small portion which will behave like a straight wire. Okay, and it's infinite. So I'll be taking a straight wire formula for it. So AB is a long wire. See, I've taken AB is a long wire, thickness dx. This part has current di because the entire current is I. So if I'm going to take only small part, it will obviously have current di. As entire PQ part has current I, I've written that. For long wire, dB at O is given by. Now for long wire, we know the formula. What is the long wire? 2K I by distance, and that is the simple formula for the long wire. Same I've written, but for differential current. So if it is I, it will be Ki by R into 2. If it is Di, it will be K Di by R into 2. Nothing changing. That's it. Just replace I with Di. Now, direction wise, as I've taken this current to be outside, I'm taking as K cap. Outside is K cap. And again, I've taken the local direction, local XYZ I've drawn. If this is plus K, this will be plus I. Okay. So I've taken that the axis like this. Okay. The outside is plus K, this is Y, this is X. So if this is taken plus K, the right side towards the point of interest is I cap. I've taken that. So dB will be 2 K diy and K cross I is J. This part is done. So whenever you see a symmetric figure, always go for the exactly opposite element in all such questions. So I've gone to now A dash B dash element and found the magnetic field. Now plus J is obviously where I've taken this local direction. So plus J is calculated like this dB. Okay. Now let's go again back to this. The formula will obviously be same. Little bit direction is changing. Why? This is plus K upwards. And now if I'm taking this as my XY axis, this is Y, this is X, this will be minus X. And we have taken minus I. So this time I'll get minus J. dB you can see here, 1 dB you can see here. I have not drawn both in the same diagram because then it will create confusion. So I have drawn both in the different diagrams. This is dB. Now if you see, 1 dB component will be upwards and one will be in the left direction. Similarly for this, one will be downwards and another one will be same left direction. That means this horizontal components will be added. Here this is phi angle. So sin theta component will be upwards, and this is phi. And as we know, this position vector minus I which we have taken to it, this angle has to, this arrow has to be 90 degree. Phi has been taken. This is 90 minus phi. This is phi. So here also the cos phi component is getting added and sin phi is going downward, which is opposite to the left case. So sin components will be cancelled out. dB sin phi cancels out and dB net is dB cos phi. So B net, total B will be dB cos phi integration. Let's see how to solve it. So I've again drawn the diagram for clarity. This is dB, dB cos phi, dB sin phi, dB cos phi and dB sin phi. Sin phi gets cancelled, so we get B equals to dB cos phi. Now I'm opening the formula. dB is K di, 2K di by R. Now 2K can be written as mu naught upon which I've solved first here. So see how I've solved for di. Very important. How to solve for di? This entire semicircular part cross section had a current I. So we can use unitary method that when this part is of pi radian, the angle is I. So if for very small angle, as I've taken in this, for very small angle, see, this is a very small angle, d phi. This is d phi. So if this entire phi, the entire pi radian has current I, so very small d phi will have current how much? We simply use by unitary method. So pi, angle subtended is pi, then current is I. If the angle subtended is d phi, the current will be I upon pi d phi. So dB equals to 2ki pi r d phi, because I just need to plug in the values of di here, and this is the value for di, the current in the part subtending d phi angle, that is di. Okay, so I've simply put the value of di here, and 2k by r is intact, and di is I upon pi into d phi. Don't get confused, clearly see it. Now dB is, I'm opening now 2k. If I open 2k, that means upon 2 pi, and 1 pi gets multiplied, so I get a pi square I d phi by r. Everything is constant except d phi, so that d phi will be taken into the integration, and cos phi will come as it is. So mu naught I upon 2 pi r square is taken, and cos phi d phi will be integrated from 0 to pi by 2. Now if I'm taking only 0 to pi by 2, that means I'm only solving 1/4. 0 to pi by 2, I'm only solving 1/4. So in the end I'll multiply by 2, because we have both the quarters contributing to the field. So first I'm doing 0 to pi by 2 of cos phi d phi. This is the integration of cos phi, that is sin phi. Plugging the value sin pi by 2 minus sin 0, you get this. And for both the coordinates, you multiply by 2 and you get to the answer.